This video goes over the concept of polar coordinates and graphing with polar equations. Now, we're going to take a look at the polar coordinate system. Normally, what we deal with is what we've been calling the rectangular coordinate system, where we find points by using X and Y. X is traditionally a left-right movement, and Y is an up-down movement. And that's how we essentially give directions when we're mapping out a point on the XY axis. We say how far in the X direction do we move, how far in the Y direction do we move. The polar coordinate system does something different. It gives two pieces of information as well, but it gives a distance and then an angle direction. That angle is going to be measured from the x-axis. So it says, for instance, go out 5 units at an angle 90 degrees from the x-axis, or go out 7 units at an angle 125 degrees from the x-axis. Usually in this class, since we're going to be dealing with calculus topics, our angles will be in radians. So instead of 90 degrees, we'll say go pi over an angle of pi over 2, or other angles as well, like 3 pi over 5 or something like that. But distance and direction are what we're going to use. The distance measured from the origin and the angle measured from the x-axis. Now, the right triangle is actually going to give us all of the information we need. When we do conversions between rectangular coordinate system and the polar coordinate system, back when we looked at, or hopefully you looked at some point in your mathematical career, the right triangle. The right triangle has this SOHCAHTOA property, which means the sine of the angle here, this angle, is equal to the opposite side length divided by the hypotenuse length. Cosine of that angle is equal to the adjacent side length divided by the hypotenuse length. And the tangent of the angle is equal to the opposite side length divided by the adjacent side length. And if we do this in the rectangular coordinate system, we get some interesting things. Let me draw it in the rectangular coordinate system just so that we have it. So the angle that we're talking about is the one that goes from the x-axis to this ray, starting at the origin to our point. So that's the angle that we're talking about right here. Okay. The polar coordinates are going to give you that angle and the distance of our hypotenuse, which we tend to label as r. Now, if we're at a point over here, the x value is going to be how far from the origin to here. So the x value of that point, the y value of that point is going to be the distance along this leg of the right triangle. So x value of the point gives you this leg of the right triangle, y value gives you this leg, and the r for polar is given by the hypotenuse. So in our cases, when we look at SOHCAHTOA, well, the sine is going to be opposite, which is y, divided by hypotenuse, which is r. So sine of theta, we'll call this theta, is y over r. Cosine is going to be x over r. Cosine of theta, that is. And tangent of theta is going to be y over x. So SOHCAHTOA gives you that, and then obviously we have the Pythagorean theorem, which says on a right triangle, the first leg squared plus the second leg squared equals the hypotenuse squared. So we have that as well. And if I want to write this point, no matter where it's located, you can, move this around anywhere you want. That's going to be the case. Now I've drawn this point obviously in the first quadrant. You could pull that point into the second quadrant or into the fourth or into the third quadrant if you like, and you just get a different right triangle. But anywhere you want to pull that point will work like that. SOHCAHTOA will apply. Now, if sine of our angle theta is actually equal to y over r, and if cosine of theta, like we said, is equal to x over r, and we had tangent of theta equaling y over x, and then the last property was the Pythagorean theorem, which said x squared plus y squared is equal to r squared. Then these four equations can be rewritten as conversion equations. In other words, if I have x and y, I can use these bottom two equations to find theta and r. If I have theta and r, then I can use these top two equations to find y and x. And that's traditionally what we do. We say this top equation, we use that one to find y. So let's solve it for y. You just have to multiply times r on both sides. You'd get y equals r multiplied times the sine of theta. And then in this next equation, you usually find x when you're dealing with that second equation. So we rewrite that as x equals r multiplied times cosine of theta. Now on these bottom two equations, usually we find theta with this equation. If I'm given x and y, I use this equation to solve for theta or to find theta. Now, you could say theta is equal to inverse tangent of y over x. There's a little bit of a problem with that. So usually when we deal with this equation, we deal with it exactly in that form. We usually say tangent theta is equal to y over x. And we'll use that later and you'll see why we do that. In this last equation, basically most times we just put the r squared on the left. So r squared is equal to x squared plus y squared. These four equations allow me to convert back and forth between polar coordinates and rectangular coordinates. So I get this triangle, or any triangle, but in particular this one, where x and y give us this, r and theta give us this. If I want to give this point in rectangular coordinates, I'd give you the x and the y. If I wanted to give you this point in polar coordinates, I'd give you the r and the theta. That is, theta is always going to be measured from the x-axis to this ray. So that's the idea. And now we have these four equations that convert back and forth. If I give the xy, now I can find the r and the theta. If I'm given the r and the theta, now I can find the x and the y through those four equations. That's essentially what this next slide says. If we want to go back and forth between rectangular and polar, if you're given polar, r times cosine theta is going to be the x value, r times sine of theta is going to be the y value. And then if you wanted to find r, usually we write the equation like this, r squared is equal to x squared plus y squared. If we want to find theta, we know that the tangent of theta is y over x. So if you're given x and y, you can find theta here. If you're given x and y, you can find r with this. If you're given r and theta, you can find x with this one. If you're given r and theta, you can find y with this one. So that is a pretty straightforward conversion for going from rectangular to polar or polar to rectangular. Now we can convert both points and equations. Let's start out by converting points. Let's take some polar points and convert those to rectangular points. If you want to try a few of these on your own, feel free to do so. Just push pause on the video and realize that every time we're doing this, we're using radians. And so make sure your calculator is in radian mode. These 4 points are in polar form, so we want to convert them to rectangular form. So let's go ahead and do that. In rectangular form, well, I'm looking for an x value and a y value. And from our conversion equations, the x value is going to be given by r times cosine of theta. The y value is going to be r multiplied times sine of theta. So in this first case, that is going to be 8 multiplied times the cosine of pi over 2. For the x value. For the y value, we get 8 times sine of pi over 2. Now you can plug those into your calculator. You can look at a unit circle calculation, anything you want, but cosine of pi over 2 is 0. sine of pi over 2 is 1. So we just get 0, 8 as our rectangular point for this polar point. So if this polar point is r theta, then the x is 0, the y is 8. That should make sense graphically. We're moving along the in the pi over 2 direction, and we're moving 8 units. So if you think about a typical point, moving in the pi over 2 direction is moving up the y-axis. And again, pi over 2, that's the angle, 90-degree angle. So we're moving up the y-axis, and we're moving up 8 units. Along that y-axis. So we should be getting at the point 8, or excuse me, 0, 8 right there, which it is, as you see. So we're moving up the y-axis. That's a pi over 2 angle. And 8 units. So we're at 0, 8. Now we can do that calculation for any of these points. So the next point in rectangular coordinates, we would get 4 times cosine of negative 7 pi over 6. That's going to be our x value. And our y value would be 4 times sine of negative 7 pi over 6. This is something I would probably just plug into my calculator. Obviously, when I plug in negative 7 pi over 6 into cosine, I'm going to get kind of an ugly number. So I'll use a rounded version. Maybe I should use approximately there. So that is right about negative 3.46 as an x value. And then as a y value, I get 2. You could, if you looked on the unit circle, get the exact value if you wanted. On the unit circle, if you looked at this, you would end up with, I believe that is 2 times the square root of 3. So you get root 3 over 2. I'm sorry, not 2, negative 2 times the square root of 3 as your x value. And then obviously 2 is your y value. So if you're looking for the exact answer, negative 2 times the square root of 3 is that. And again, you could find the exact answer using the unit circle. The fact that cosine of negative 7 pi over 6 is root 3 over 2, then multiply that by 4, you get negative 2 root 3. Usually I have people plug in a decimal version approximation. By the way, let's think about this situation for just a moment. 4 and then negative 7 pi over 6. Negative 7 pi over 6, where we can think about where that is in relationship to our angles, and then go out 4 units. So negative 7 pi over 6, well, if you think about negative 7 pi over 6, that's a negative angle. So we have to start measuring in this direction. We're going to go around in a circular shape a little more than pi. So we're going to be out here, and we need to be going about 4 units out. So a little bit more than pi and about 4 units out is what's happening. So that's what's going on. And by the way, when we say going negative 7 pi over 6 and 4 units out, this is kind of like having a circle of radius 4 and moving along that circle of radius 4 until I hit the angle of negative 7 pi over 6. That's more than pi. Excuse me, I should say more than pi in absolute value. So we start negative angle moves clockwise. Positive angle would move counterclockwise. But negative 7 pi over 6 we move clockwise, 7 pi over 6 units, angles, radians. And then we're moving out 4 units, and we get to that point there, or something close to that point anyways. And again, this point is in the second quadrant here. Quadrant 1, 2, 3, 4. So this is a quadrant 2 point. Let's look at the next point, negative 8 of comma 3 pi over 2 in polar. We take negative 8 times the cosine of 3 pi over 2. That would give me my x coordinate, and then negative 8 times the sine of 3 pi over 2. That would give me the y coordinate. By the way, with 3 pi over 2, when you plug that into cosine, you get 0. When you plug that into sine, you get negative 1. So negative 8 times negative 1 gives you a positive 8. Notice that we got the exact same point we did in our first calculation. We got the x coordinate to be 0 and the y coordinate to be 8. But we used a different r and a different angle. This can happen a lot. We can have lots of different angles that give us the same point, because anytime you add on 2 pi, for instance, if you take 8 and then comma pi over 2 plus 2 pi, you've gone around the whole circle and again and ended up at the same point. Pi over 2 and pi over 2 plus 2 pi are coterminal angles, meaning the ray is on exactly the same. So you can always add 2 pi, but notice that pi over 2 and 3 pi over 2 are a difference of pi, and here we used a negative r. Let's think about what that means. So the angle here is 3 pi over 2. If you think about 3 pi over 2 as an angle, and again, rotating around a circle, we get this angle that's this ray that's pointing down. So we have this ray here that's pointing down. Now, if I'm traveling along that in a negative direction, an r of negative 8 would say, instead of moving down 8 units, go in the opposite direction 8 units. So instead of moving down, we're moving up 8 units. And so that's why the negative R value is going to be shooting in the opposite direction. So 3 pi over 2 goes, again, 3/4 of the way around in a circle. And normally with a positive R, I'll be moving down, but with a negative R, I'm moving in the opposite direction. So I'm moving back up. And that's why we end up at 0, 8. Let's take a look at this next point. This point, 3, 2.71, again, is in polar coordinates. If I want to convert this into rectangular coordinates, all I have to do is plug in 3 times cosine of 2.71 for my x value, and then plug in 3 times the sine of 2.71 for my y value. In this case, I just use my calculator. We're not going to get a really nice value, so it'll be probably just an approximation that I'll give. I end up with about negative 2.72. That's my x value. And my y value is a positive 1.25. Now, notice that in each of these cases, I've been doing a lot of explanation, but in reality, if we're just converting to rectangular, all we really have to do is plug in our cosine theta for x, plug in our sine theta for y, and we are good to go. So just plugging it in, and obviously 2.71 as an angle is slightly less than pi, and that's why we are in the second quadrant. So what I mean by that is, again, this angle is talking about angle from the x-axis. Pi over 2 is like 1.57-ish. And then 2.71 is some angle, I'm not going to be exact here, but some angle in this. It's less than pi, which is 3.14, but more than pi over 2, so it's in the second quadrant. And then we move out certain distance and get to our point. Obviously, again, I'm not being precise when I'm drawing this. So that's how we go from polar points to rectangular points. Now let's go in the reverse. Let's assume that I'm given rectangular coordinates and I want to convert those to polar coordinates. So I have rectangular points, I want to go to polar points. Here are 4 examples of rectangular points, and I'm going to convert these to polar points. When I start at rectangular and go to polar points, I need to use these 2 equations. R squared is equal to x squared plus y squared, and tangent of theta is equal to y over x. Now, these 2 equations are going to give me some options. Obviously, if I want to, I can use negative r values, but usually we'll use positive r values when we solve this equation. So this equation will have 2 different solutions, a negative and an positive for my r, we tend to use the positive. This equation also is going to have a couple of different solutions depending on what I allow my theta to be, like the range for my theta. We'll get into that in just a second. So in this case, where I have 2 comma 2, I would say that the r squared is equal to 2 squared plus another 2 squared. You can put that in parentheses if you'd like. So we'd have r squared is equal to 8. And I would let r be the square root of 8. And normally what I do is let r be equal to the positive square root of 8. Again, I use positive r values generally. Now, for this one, we know that tangent of theta is going to be equal to 2 over 2. When I go ahead and solve for that, let me go ahead and solve for that. I would do the inverse tangent, excuse me, is the actual value for theta. Now, the reason why I'm doing this, and I'm being a little bit careful here, so the inverse tangent of 2 over 2 is equal to theta. That is because I know this point is in the first quadrant. When I type in inverse tan of 2 over 2, I get roughly 0.79 as my theta. So that means that this rectangular point in polar is going to be approximately square root of 8 for my x value. Well, let's take an equal exactly. This point is going to be the square root of 8 for the x value, and then inverse tangent of essentially 1, 2 over 2 is 1, inverse tangent of 1 as my y value. Square root of 8 is about 2.83. As already said, inverse tangent of 2 over 2 is about 0.79. And we're good to go. So that is the polar point. The fact that my theta was equal to the inverse tangent does rely on the fact that this point is in the first quadrant. In order to show what's going on, let's do the next example. In the next example, we have a point in the second quadrant. So let me, quadrant 1. This is in quadrant 2. The r is going to be calculated the exact same. R squared is equal to x squared plus y squared. X here is 3, Y here is 4. So we get 9 plus 16. Square root of 25 is 5. So we're going to be using R equals 5. I tend to use the positive R value. Okay. Now, tangent of theta is going to be y over x. In this case, that's 4 divided by -3. So because of the nature of inverse tangent on our calculator, if I just did the inverse tangent of 4 over -3, that thing would give me a negative 0.93 approximately. Negative 0.93 sends us into quadrant 4. So what I'm saying is think unit circle. We are starting at along the x-axis, and a negative 0.93 shoots us into this direction. It shoots us into quadrant 4. We actually wanted to be in quadrant 2. We knew that because of the point we had. It was -3, 4. So wait, it's going to be shooting way up there. But my inverse tangent got us into quadrant 4. Now, the reason for that is because the point 3 comma -4 would have the exact same inverse tangent. Think of a positive 4 over a -3 is going to give us the same thing as a -4 over a positive 3. So essentially, what we need to do is we need to go in the other direction, the exact reverse direction. There's 2 ways to do that. One is just to add pi. If you add pi to that, then we get a 180-degree turn. And if we add pi to that, we can use a positive r. The other way to do that is to utilize a negative r that would go in the other direction. I tend to add pi so that I can keep the positive r value. So hopefully that makes sense. In order to get into quadrant 2, we need to add pi to our inverse tangent. So that's what I do. Since we're in quadrant 2, in order to get my theta, I take the inverse tangent and then I add pi to that. And so we are going to be at the point 5 comma, the r value is 5, and then the theta is going to be inverse tangent 4 over -3 plus pi. And usually I would give an approximation for that. Five is obviously just the R value, and the approximation is about 2.21 when I type this into my calculator. So if we're in quadrant 1, we just use the inverse tangent. If we're in quadrant 2, we use the inverse tangent and then plus pi. If you want to try these next 2 points on your own, push pause on the video. In a couple of seconds, I will show you how these are done. Okay, so we're going to do them the exact same way we did these. First, I want to first notice, though, that -1 comma √3 is in quadrant 2. Inverse tangent gives me out angles that are not in quadrant 2. They either give me out angle, it either gives me out an angle that's in quadrant 1 or an angle that's in quadrant 4. That's not going to affect the R. We still have to find R by taking R squared is equal to, in this case, -1 squared plus the square root of 3 quantity squared. So that means R squared is going to be equal to 4. So I'm going to use R of 2. I always use positive R's. Now, tangent of theta is going to be equal to square root of 3 over -1. Because we are in quadrant 2, that means my angle theta is going to be the inverse tangent of √3 over -1. I'll just call that negative square root of 3. And then I'm going to have to tack on a plus pi. And I'm tacking on a plus pi because if I just looked at the angle that I got when I do inverse tangent of negative square root of 3, I get negative 1.05 roughly, which is in quadrant 4. So when I add pi to that, I get back into quadrant 2. I'm just going to give an approximation of my answer so I don't have to write so much. Obviously, R is 2. And then I get about 2.09 as my angle theta. By the way, if you don't recognize this, this is actually negative pi over 3. So that's negative pi over 3 if you were looking to be really exact. Similarly, with this last point is in quadrant 3. When I find R, That's the easy part. R squared is equal to -4 squared plus -2 squared. That's R, excuse me. When I solve that, R is going to be equal to the square root of 20. And then tangent of theta is going to be equal to, well, y over x in this case is -2 over -4. Notice that's the exact same thing as +2 over +4. Since we are in quadrant 3, theta is going to be the inverse tangent of, again, think of it as 2 over 4. If I just type in inverse tangent of 2 over 4 or inverse tangent of -2 over -4, I get an angle in quadrant 1. If I want to be in quadrant 3, but I'm in quadrant 1, I just tack on a plus pi. Hopefully that makes sense. Inverse tangent is giving me this angle, which gets me to this point, and I want to go in the exact opposite direction. I want to get to the point, what was that, -4, comma -2. So I want to go in the exact opposite direction. So to go in the exact other direction, add pi, and then we'll be headed in the correct direction. If I want to give the, again, the point approximately, obviously exactly it's these two, r and theta are there, but that's the point approximately. Root 20 is about 4.47. And inverse tan of 2 over 4 plus pi is about 3.61. So that's the point I'm getting. If I start with this rectangular point, then this is the corresponding polar point. There you go. As you can see, whenever you're in quadrant 2 or quadrant 3, you're going to have to tack on a plus pi to your inverse tan. If you're in quadrant 1, you can just use inverse tan by itself. If you're in quadrant 4, you can also use inverse tan. So a lot of times when we're dealing with polar coordinates, what we'll say is force r to be positive, and then this theta is between -pi/2 and 3 pi/2. That basically is exactly what I'm doing here. So if we're in quadrant 4 or quadrant 1, inverse tan gives me exactly what I want. If we're in quadrant 2 or quadrant 3, then I have to do inverse tan and then tack on a plus pi if I'm using a positive r. That is how to convert points to points. We've converted rectangular points to polar points, and also polar points to rectangular points. The polar to rectangular is a little bit more direct because I don't have to worry about that inverse tangent versus inverse tangent plus pi. Now what we can do is start converting between rectangular and polar equations. Let's take a look at this rectangular equation. That is a rectangular an equation written in terms of x and y. And let's convert that to an equation in polar form written in terms of r and theta. Whenever we do this conversion or any conversion, we start by looking at our four conversion equations. Y equals r sine theta, x equals r cosine theta, tangent theta equals y over x, r squared equals x squared plus y squared. When I'm going from rectangular to polar, I can always replace every y I see with r sine theta, and I can always replace every x I see with r cosine theta, and then try to simplify as best as we can. However, you can also utilize these other two. If I have a y over x, I can change that into a tangent of theta. If I have an x squared plus y squared, I can change that into an r squared. So while you can always replace every x you see with r cosine theta and every y you see with r sine theta, you can also use these other two, and sometimes these other two make the conversions a little bit quicker. That's the case in this example. In this example, we have an x squared plus y squared. The quickest way to do this is to say, well, that means r squared is equal to 25. So we just replace the x squared plus y squared with an r squared, and now we have a polar equation. Now, a lot of times with our polar equations, we tend to solve for r. Just like in our rectangular equations, we like it when we have y as a function of x. In polar equations, we like it when we have r is equal to a function of theta. In order to solve this, all I have to do is take the square root of both sides. And you might say, well, can't r also be -5 as well? R could be -5, but remember, based on how we did our polar coordinates, we can always use positive r values if we want, if we just use a different angle. So if I wanted to use an r of -5, I could use an r of +5 with a different angle. This is my polar equation, r equals 5. Notice that x squared plus y squared equals 25 is a circle of radius 5. A circle of radius 5 in polar equations is just r equals 5. By the way, in Desmos, you can graph polar equations by just using r. So I used r equals 5, and I got this nice circle of radius 5. You can also do that on the TI-84. I'm not going to show you that in this video, but I will put a companion video up on how to graph using the TI-84 with polar equations. Let's look at a couple more. Let's convert this rectangular equation, which is a equation of a line, to a polar equation. It is y equals 3x minus 2. And so that I don't have to go back to these slides, let's also convert the rectangular equation x squared equals 16y to a polar equation. When I do this, I'll solve for r in both cases. If you want to try these two cases on your own, push pause on the video. In a couple of seconds, I will do these and show you how that's done. Let's do y equals 3x minus 2 right now. Y equals 3x minus 2 is not going to fit an x squared plus y squared form very nicely. It's not going to have y over x. So when in doubt, just replace every y I see with r times sine theta and every x I see with r times cosine theta. When you do that, you get r times, sine of theta is equal to 3 times r times cosine of theta, and then minus 2. Now I have this equation written in terms of r and theta. Usually we solve for r when we can. In this one we can. So I'll go ahead and do that. If I solve for r, the first thing I want to do is subtract 3r cosine theta from both sides. That'll give you 3 times sine, not 3, r times sine of theta minus 3r times the cosine of theta is equal to a negative 2. And now what I do is I take this equation and on the left-hand side, I factor out an r. If I factor out an r from the left-hand side, I just get sine theta minus 3 cosine theta. That whole quantity times an r is equal to negative 2. This means that I can divide both sides by that big quantity, sine theta minus 3 cosine theta. That'll give me r is equal to the fraction whose numerator is negative 2 and whose denominator is sine of theta minus 3 times the cosine of theta. So this is the equation of this line in rectangular form. So we have the line in rectangular form, which is y equals 3x minus 2. In polar form, it is r equals a fraction whose numerator is negative 2 and whose denominator is sine theta minus 3 cosine theta. So that's basically it. Now I want to point out something. In our previous case, r equals 5 is a very simple equation in polar form, a lot simpler than x squared plus y squared equals 25. In this case, I would suggest that y equals 3x minus 2 is simpler than this y equals negative 2 over sine theta minus 3 cosine theta. Imagine trying to take derivatives in each of these cases. The case where we have -2 over the quantity sine theta minus 3 cosine theta, taking a derivative of that would be pretty tough. Taking a derivative of y equals 3x minus 2 is not so tough. So in this case, the polar equation was more complicated than the rectangular equation was. In our previous case, the polar equation is less complicated than the rectangular equation. And obviously, this rectangular equation, I didn't even solve for y. If I wanted to solve for y, I would have square root of 25 minus x squared, or the negative square root of 25 minus x squared, equaling y. So this shows you that some equations are a little bit nicer in rectangular form. Other equations are a little bit nicer in polar form. Here's another example where we're asked to convert to a polar equation. Here we have x squared equals 16y. That's obviously a parabola. I don't have x squared plus y squared. I don't have y over x, although I could have y over x if I wanted. But I don't have it right here. I could manipulate it to give it that to me. So since I don't have it immediately, what I'll do is I will just replace every x I see with r times the cosine of theta, and then replace every y I see with r times the sine of theta. On the left-hand side, we get r squared times cosine squared of theta. On the right-hand side, I'll just leave that as 16r times the sine of theta. If I want to solve for r in this case, I don't want to pull both terms onto the left. In this case, what I would do is I would divide both sides by r to begin with, since all of my terms involve an r squared and an r. So one of them involves an r squared, one of them involves an r. So divide both sides by r, we would get r times the cosine squared of theta. Whoops. Is equal to 16 times sine of theta. And then when I divide both sides by cosine squared, what happens is I get r equals 16 times the sine of theta on top divided by cosine squared of theta on the bottom. There's a number of ways we can rewrite that. You can think of sine over cosine to the first as tangent, and then 1 over cosine as secant. So another way to write this, if you wanted, is r equals 16 tangent of theta multiplied times secant of theta. Again, that's just some algebraic manipulation. Feel free to leave it this way as well. Now, with all of these cases, many times you can actually approach the same problem in different ways. So I do want to just point that out. Here, I replaced the x with r cosine theta, the y with r sine theta, and then I solved like normal. Another way that you could have done this is you could have divided both sides by a single x to begin with. Let me write it this way. Let's write it 16 times y over x. And then I could have said, oh, y over x is tangent. So x is r times cosine of theta. And then y over x is tangent. So that's 16 times tangent of theta. And then dividing both sides by cosine. Well, 1 over cosine is secant, so I could have rewritten this as 16 tangent of theta multiplied times secant of theta, or divided by cosine. It doesn't matter. Multiply by secant, divide by cosine, same thing. So notice that, again, in this case, dividing by x allowed me to use one of my other conversion equations. It gets you to the same place in the end. Gets you to 16 tangent theta secant theta, or if you wanted to write it in terms of sine and cosine, you could have written, even this one, you could have transformed this into sine and cosine as well. And you'd have gotten 16 sine theta divided by cosine squared of theta. So oftentimes with these problems, there's more than one way to solve. This one, probably the linear one, there's probably one good way to solve. With this equation, the circle, there's one really good way to solve, which is the way we did it. But you could have also replaced every x you saw with an r times cosine of theta. And then every y we saw with an r times sine of theta. When we do the squaring, we'll get r squared times cosine squared. That is cosine squared of theta, obviously, plus r squared times sine squared of theta equaling 25. And then I could have factored out an r squared. Factoring out an r squared, I'll do that on the same line, gives me r squared multiplied times cosine squared plus sine squared of theta. We know that cosine squared plus sine squared of the same angles give me 1. So that's just r squared times 1 is equal to 25. And then because we can use always positive r values if we want, we can have r equals 5. So this is another way to do this one. Obviously, it's easier to see in this first case, the way we first did it, than this case. This case, we have to use the identity, the Pythagorean identity on the unit circle. Cosine squared of theta plus sine squared of theta equals 1. But my point is, we use these for conversion equations however we want to. Some ways are going to be better than others. There are some scenarios in which you can kind of figure it out in two different ways. There are some scenarios where there's only going to be really one good way to do it. But use these conversion equations to going from rectangular to polar. Now, the nice thing about rectangular equations is that when in doubt, you can always replace every y you see with r sine theta, and you can always replace every x you see with r times cosine of theta. So rectangular equations, we can always go to polar equations in a straightforward manner. Always, when in doubt, replace y with r sine theta and x with r cosine theta. That doesn't mean I can always solve for r. Sometimes I won't be able to solve for r, but we can always do a conversion into a polar equation. In the other direction, you usually can do that. You usually can convert into rectangular equations, but it's not always a guarantee. The ones that I give you to do converting from polar to rectangular, it will always be doable in some way when I ask to convert. Let's look at a couple of examples. Let's start out with converting these two basic polar equations into rectangular equations. The first equation is r equals 4. The second equation is theta equals 10. These two equations should be fairly obvious, the route we're going to take to get to the rectangular equations. In the first equation, we kind of did the reverse earlier. So in the first equation, I'm going to square both sides. And then I'm going to replace the r squared with an x squared plus y squared. Now on these, I'm not going to have to solve for a single variable. X squared plus y squared equals 16. We already know that that looks like a circle of radius 4. I don't worry about solving for y. In this next equation, I just have theta. So I'm going to apply tangent to both sides. If I apply tangent to the left-hand side, I get tangent of theta. If I apply tangent to the right-hand side, I have tangent of 10. So applying tangent to both sides gives me that. By the way, tangent of 10 is around 0.65. Whoops, I will not actually, I won't actually write that as a decimal right now. But because I have tangent theta, I can replace that with y over x. So y over x is equal to tangent of 10, which remember is close to 0.65. It's just some numerical value. Notice what that is. Rethinking that or rewriting that, I just get y is equal to the tangent of 10 multiplied times x. Again, that's y equals about 0.65 times x. Therefore, this is just a line through the origin. So r equals a number gives us circles of whatever that number is as far as radius goes. And then theta equals a number gives me lines through the origin. Oftentimes people think of circles of a certain radius and then lines through the origin as our building blocks for the polar coordinate system. Every point in the polar coordinate system is on a line through the origin and at a circle of some radius. That's kind of like when we graph in um, when we graph in rectangular coordinate systems, every point is on some x equal line, that's a vertical line, and a y equals line. So if I go x equals a number, not sure why that's not working. X equals a number, something like 5, and then y equals a number, let's say it's something like -3, then we can think of traveling in the rectangle, or we can think of drawing a rectangle and getting at 5, -3. Well, in polar form, when we have y equals mx, some slope line through the origin, theta equals a number, and then r equals a number, let's say 6, we can think of going in a direction, hitting a circle. Every point in polar coordinates is at the intersection of some line through the origin and circle. Just like rectangular coordinates, it's the intersection of a vertical line and a horizontal line. With the rectangular coordinates, that's why our grid is always split up this way. We have horizontal lines that give me the y values and vertical lines that give me the x values, and that's why the grid looks the way it does. Oftentimes, when people graph in polar, they'll switch the grid to looking like this. They'll have concentric circles, and those circles are all centered at the origin or at the pole, and then lines through the origin, lines through the pole. When we graph in polar, we call the origin the pole or origin. Also, when you graph in polar coordinates, you'll call the x-axis the polar axis, and the y-axis the line theta equals pi over 2, because that's the angle you're moving at. But a lot of times when people graph in polar, they graph in a polar coordinate system, and that grid looks like this. Concentric circles with lines through the origin. And that's because that's what our building blocks are. R equals number, theta equals number. R equals number gives me a circle centered at the pole or centered at the origin. Theta equals a number gives me a line through the origin or a line through the pole. Now, most of our conversions are not going to be quite like that previous one, not just R equals a number or theta equals a number. Most of our polar equations are going to be more complicated than that. So let's practice converting polar equations to rectangular equations. We'll start with this example. R equals 7 times secant of theta. Now, there's a number of different techniques we can utilize when converting from polar to rectangular. We're going to either need a tangent theta or an r squared theta, or we could also use an r sine theta or an r cosine theta. These top two are actually the more used versions. So here we have an r by itself. If I just square both sides, I get a secant squared on the right, which doesn't do a whole lot for me. So instead of that, since y involves sine and x involves cosine, if I have another trig function like secant, oftentimes I'll write secant in terms of sines and cosines. In this case, I can write secant as 1 over the cosine of theta. Now, if I multiply both sides by cosine, I end up with r times cosine of theta is equal to 7. Now I can do a substitution. R cosine theta can get replaced with x, and I'll just end up with the equation that is x equals 7. So that's the vertical line x equals 7. And in polar form, the vertical line is r equals 7 times secant theta. So that's one technique. Convert into cosines and sines, multiplying both sides by cosine. Let's do another. Here we have r equals 8 times sine of theta. This looks fairly similar to our last one. We had r equals secant of theta, or r equals 7 secant of theta, technically. But the technique we're going to have to employ here is a lot different than the previous example. In this case, because if I divide sine, I get r divided by sine. That's not going to do me any good. If I divide by r, I get sine divided by r. That's not going to be doing me any good. I want an r times sine to have y. Now, one way I can do that, and probably the easiest way, is to multiply both sides by r. If I multiply both sides by r, I get an r squared on the left-hand side, and I get 8r times times sine of theta on the right-hand side. On the right-hand side, that r times sine theta can turn into a y, and on the left-hand side, the r squared can turn into an x squared plus y squared. So here we get x squared plus y squared is equal to 8 times y. Now, I won't go through the details. You can complete the square if you want, but this is actually a circle. And it's a circle that's along the y-axis, or along the theta equals pi over 2 line. So that's what this is. It's going to be a circle of, I believe, yeah, radius 4 along the y-axis, or y over 2 line. Or theta equals pi over 2 line, excuse me. The y-axis is the line theta equals pi over 2 in polar equations. But yeah, that's a circle. Let's do this one. R equals 12 times tangent times secant. That is tangent of theta times secant of theta. There's a couple of different ways we can do this. Obviously, we can use tangent theta as y over x anytime we want. Secant, I would probably write as 1 over cosine so that I can employ that same technique we did in 4b, which was multiplying both sides by cosine. So let's do this one. Again, one way to do this is not the only way to do this, but one way to do this is to leave tangent of theta alone and replace secant with 1 over cosine of theta. And then I can multiply both sides by cosine. If I do that, I get r times the cosine of theta is equal to 12 times the tangent of theta. And then I would end up with x equals 12 times y over x, or 12y over x. And then if we wanted to, we could multiply both sides by x and get x squared is equal to 12 times y. Obviously, that's a parabola. We kind of did the reverse earlier, although with a different coefficient out front. We did a very similar thing earlier. And just like earlier, this is not the only way you could have done this. One way you could have done this is convert the tangent and the secant into all sines and cosines. If you did it that way, then what you would get is r is equal to 12 times sine of theta divided by cosine squared of theta. And then maybe multiplied both sides by cosine squared, you would have ended up with r times cosine squared of theta is equal to 12 multiplied times sine of theta. And then multiplied both sides by r. If I multiply both sides by r, I'm just going to copy and paste. Multiplying both sides by r would give me r squared on the left-hand side, and then r times sine theta on the right-hand side. And this is the same equation. Now, r squared times cosine squared is r cosine quantity squared. So we get x squared is equal to 12y. Again, just another way to do the same thing. So whichever approach you use, you'll get the same thing at the end, x squared equals 12y, when you do that conversion. This shows that there's a number of approaches. Sometimes there's going to be multiple of approaches. Multiplying r by both sides is a technique you can use. Dividing or multiplying by cosine or sine is a technique that you can use. We saw earlier that we squared both sides. That was a technique that we can use. We can apply tangent if I just have a lone theta around. But like I said at the very beginning, while these equations you can convert nicely into a rectangular equation, there are some polar equations that are going to be very hard to convert into a rectangular equation. Take, for instance, the equation r equals theta. That would be extremely difficult to convert because if I square both sides, then the r squared works out nicely. If I apply tangent to both sides, then the right-hand side works out nicely, the left-hand side does not. There's no trig function of theta, so if I apply sine or apply cosine, it's fairly difficult to deal with. So this one would be tough to convert into rectangular, okay? So the ones I give, you will be able to convert. Other ones may be tougher to convert. In the last part of this section, we're going to sketch some polar graphs. I've already said that usually when we think about sketching polar graphs, we write them as r equals a function of theta, just like a lot of times when we write rectangular coordinate system graphs, we write as y equals a function of x. Now, if we are going to graph, there's a few different ways we can graph. Obviously, we can plot out some polar points if we want, plug in different values of theta, and then plot the points. We can convert from polar into rectangular coordinates and then graph using the normal rectangular coordinate system, or we can use technology. For the most part in this section, I'm going to just use technology. And obviously, we could have plotted points. We could have converted to rectangular. We've done that already. We've done the conversions already, so we already know how to do that. Plotting points is fairly straightforward. So a lot of this will be using technology. So let's sketch some graphs. And again, I'm going to use technology. In this case, I'm going to use Desmos, but there'll be a companion video that shows how to graph in polar coordinates using the TI-84 as well. Now, the first equation that was on the slide was r equals 8, which we already know is a circle of radius 8 and centered at the origin. Again, the origin is often called the pole in polar coordinates. The x-axis is often called the polar axis, and the y-axis is called the line theta equals pi over 2. So r equals 8 gives a circle of radius 8, and obviously we can change that circle to any radius that we want. If I put r equals a negative number, it's the circle of radius absolute value of that negative number. So let's move on to the next equation. The next equation was 7 times cosine of theta. Notice that 7 times cosine of theta is a circle laid out along the x-axis. one point on the circle is at the origin, and then the radius is actually 3.5. But that means the diameter stretches from the origin or the pole to the rectangular point 7, 0, which interestingly enough is also the polar point 7, 0. 7 is the length, and then 0 is the angle degree. And if you change that from 7 to any other number, let's say we change it from 7 to 12, then the circle stretches from the pole or the origin to the point 12, 0. If I put a negative number out front, then all we're doing is flipping the circle about the y-axis. So now the circle still is along the x-axis, but stretching from the origin to the point -12, 0. If I change cosine into sine, then instead of the circle being laid out in line with the x-axis, now the circle is laid out in line with the y-axis. And no matter what number we have out front, like 112, let's say, obviously if I do a 112, it's going to go from the origin to 0, 112. The equation that we were asked to graph is this one, r equals 9 times sine theta. If you use a negative number out front, just like the previous case with cosine, it flips over an axis, but this time it flips over the x-axis. The equation that I said was really hard to convert into a rectangular equation was r equals theta. Now, when you're graphing with Desmos, theta, you have to give bounds on theta. I tend to go from 0 to 2 pi. If you go from 0 to 2 pi, you get like one loop of a spiral with r equals theta. If you go from 0 to 12 pi, you get like 6 loops. But we get this spiral shape if r equals theta. You can see this is obviously not a function in why it can't be written as a function of x because it fails the vertical line test. But it is a function in polar. R is equal to a function of theta in polar. So that's what we get. Get an interesting thing. By the way, you can put in any coefficient you want. Then your spirals just get bigger or smaller depending on which coefficient you use. Putting a coefficient of 0.2 makes our spirals tighter. And then this pattern would go on forever. Obviously, I only went from theta from 0 to 12 pi, but you can go on further. Also, if you use negative values on your angles, then you just get a spiral in the other direction. So if we use negative angles, then we get a spiral in the other direction. Using example 5, we can see that in general, if I want to graph a circle with polar graphs, we see at least 3 ways to do it. There's more than 3, but we can see 3 ways to do it. R is equal to some number, like R is equal to 5 would give you a circle of radius 5 centered at the origin or the pole. We can see r is equal to a times cosine theta will give you a circle stretched out along the x-axis. So a circle, but laid out along the x-axis. I shouldn't say stretched. Laid out along the x-axis. R is equal to a sine theta gives me a circle laid out along the y-axis. And then r is equal to theta, or r is equal to some value times theta, gives you this spiral. That's actually called an Archimedean spiral from Archimedes, right? So Archimedean spiral, or just spiral. Let's look at some other well-known polar graphs. So in this case, we have 4 graphs that are a number plus some number times cosine theta. In this first one, you can see 4 is bigger than 3. In the second one, we have the two numbers equaling. In the third one, the coefficient of cosines bigger than the constant. And then we'll use sine as well when we go through that. So let's graph these using technology. Once again, I'll use Desmos, but you can also use your calculator. So r is equal to 4 plus 3 times cosine of theta. That gives us this shape. It kind of looks like almost a kidney shape. It's circular in nature, but it has a dimple on this left-hand side. By the way, as the 4 gets bigger, so let's say 4 goes to 5, then that dimple is less prominent. And as you get 6, 6 is exactly twice 3. You see that it's not dimpled at all, but just a straight line. And then if you get bigger than 6, let's say 8, then we're moving out. Again, not dimpled at all. So it's dimpled for certain values. And as we get the ratio of our constant and the coefficient of cosine gets bigger, then it gets less and less dimpled. Now, it gets more and more dimpled. So we started with 4 with a dimple. If we take 3.5, then that dimples more. Down until we hit the number 3 exactly. Once we hit where the constant and the coefficient on cosine are the same, then our curve here goes around past past the y-axis on the left, and then comes back and touches the origin or touches the pole, and then back out around. When that constant starts getting smaller than 3, so for instance, when it gets to a 2, then it goes so far back that it starts looping around. So I get this thing with an inner loop in this case. Now, there's a lot of things we can do to play around with flipping this. One thing you can do is instead of using a +3, you can use a -3. That'll flip back and forth, in this case, across the y-axis. If I used a -2 as well, that actually doesn't do much. Doesn't change anything. So using a +2 and -2 doesn't change. But again, going from positive to -3 flips back and forth across the x-axis, or across the y-axis, excuse me. Now, if instead of using cosine, we use sine, then that same object is just oriented along the y-axis instead of oriented along the x-axis. So it's basically looks like a 90-degree turn. And once again, this number being smaller than this number, the constant being smaller than the coefficient on sine, forces an inner loop. If they're equal, then it's going to go touch the origin or the pole. If the constant is bigger than the coefficient on sine, then we're either going to get this dimple shape or it's going to be a smooth shape, depending on the ratio between that constant and the coefficient on sine. If that ratio is 2 or more, then we get a smooth shape. If it's between 1 and 2, then we get a dimple shape, a dimple of some sorts. And once again, using a negative coefficient just flips that curve around the x-axis. Using example 6, we can see what is going on. Now, these are called limosons, all right? It's kind of a French term. Sometimes there's an accent on this C, but it's like a lemon and then song, all right? So limosons. But these equations are where we have A plus or minus B times cosine theta are equaling R, and R equals A plus or minus B times sine theta, where A and B are both positive. Again, we saw that it didn't matter if A was negative or not, but there you go. Now, the reason I want to say that both of these are positive is because we get that lemma song with an inner loop if B is bigger than A. When B is equal to A, that's where it went back and hit the origin or went back and hit the pole. And that particular limison is called a cardioid. When those two numbers are the same, we get a cardioid. And the root word there is related to the fact that it looks like a heart shape. So cardioid because it looks like a heart shape. Limousin because think lima bean, all right? And then obviously, if A is bigger than B, if our constant is bigger than our coefficient, then it could be dimpled or convex. It's convex if the ratio is 2 or more. It's dimpled if that ratio is less than 2. So if A, the constant part, is bigger than B, but the ratio is less than 2, then it's a dimpled limousin. And if it has ratio bigger than or equal to 2, then it's convex. These are really unique graphs, and they're actually would be very tough to graph in a rectangular coordinate system. In polar coordinates, they're pretty straightforward, but in rectangular coordinates, they're hard to deal with. Let's look at some other graphs. Let's look at another type. This is R equals 3 times cosine of 5 theta, and then R equals 10 times cosine of 7 theta, 6 times sine of 4 theta, 6 times cosine of 4 theta. These examples are going to be in another sort of class of graphs. And let's start plotting these using technology as well. Again, I'm using Desmos. You can use your calculator if you want. When we have r equals 3 times cosine of 5 theta, we get this. Notice that this looks like a flower. We call this a rose curve, and it has 5 petals on it. This rose curve is the one that is encircled by a circle of radius 3. So notice that if you draw a circle of radius 3, that rose curve is completely inside that. Now, if we switch up the coefficient out front, let's say we put it as a 10, then now that rose curve is going to be within the circle of radius 10. What's going to happen if we switch that 5 to a 7? Well, instead of getting a 5-petaled flower, we get a 7-petaled flower. And so that's what's going on. What if I switch the 7 to a 9? Well, I get a 9-petal flower. All, again, since I have coefficient of 10 there, all within the circle of radius 10. All those petals are drawn within that circle. And you could get really crazy on this. Let's say we go 15 theta on the inside of our argument. We'd end up with 15 petals. Okay. Now, notice that all of the numbers I put in front of theta, the numbers on the inside of the argument, were odd. If I make that odd number 1, this is just a single circle. So we only get one circle. If I had 3, I'd get 3 petals. 5, I'd get 5 petals. Now here's the weird thing. What if I put something even? So what if I took 6 times cosine of 4 theta? Well, if I put a 4 theta in there, I don't get 4 petals. I actually get 8 petals. If I put a 2 inside of there, I get 2 theta on the inside of my argument, and that gives 4 petals. If I put a 6, that would give me 12 petals. And since, well, let's do 8. That would give me 16 petals. Just like before, all 16 of those petals are within the circle of radius 6. Now, what if we do sine? Actually, let me do lower number of petals so we can see this a little bit easier. Let's do 5 petals. What if I change from cosine to a sine? I want you to notice that with cosine, one of the petals is aligned along this x-axis. If I change from cosine to sine with an odd number, then one of the petals is going to be aligned along the y-axis. If we have sine of 4 theta, that's going to cause 8 petals. Notice that no petal is sort of stretched out along the x or y axis. But when I take cosine, I have petals along the x-axis and petals along the y-axis. So going from cosine to sine is just a rotation of this object. So example 7 shows a lot of well-known curves, and they all fall into this class that we call rose curves. Rose curves are curves which are r equals a coefficient, a, times cosine of n theta, or r equals a multiplied times sine of n theta. N here is going to be a whole number with Rose curves. So if I want to get a Rose curve with a whole number, then this was what it looks like. And when n is odd, I get the exact same number of petals. So when n was 5, I got 5 petals. When n is even, I got double the number of petals. So when n was 2, I got 4 petals. When n was 4, I got 8 petals. Again, these are called Rose curves, and they're very interesting graphs. Other interesting graphs, well, what if we had, instead of a Rose curve with a whole number, what if we had a fraction as the n? So instead of n being whole numbers, what if we let those things be fractions? Well, with what do we call fractional Rose curves, we get some really interesting loopy shapes. I say loopy because when you draw the curves, they make a lot of loops. So let's play around with this. Let's take 6 cosine 4 theta, and instead of just having 4 theta, let's do theta over, I'll do a 12. Now, you may want to increase the bound on your theta. Notice that if I just let theta go from 0 to 2 pi, then this thing doesn't meet up. But it'll keep looping and doing some interesting things as you get a higher and higher bound on your theta. So 4 does kind of 2 loops. Once we get to 6, we've hit the origin. And then beyond there, now we're going back and traveling in the same way. Notice that the reason for this is because of the nature of cosine. Cosine is periodic with a period of 2 pi. So if I just go from 0 to 2 pi, the only angles that I've really plugged in are from 0 to pi over 6 because we're dividing that angle by 12. So when I do theta over 12, I probably want to go out to at least 24 pi, so I get the entire period of the cosine function. If I do that, I get this really strange looking object. Again, lots of loops and just keeps looping and looping and looping. Now, what if I did 2 theta over 12? Well, then I get less loops. By the way, 2 theta over 12 is like theta over 6. What about 3 theta over 12? Well, then I get these strange looping objects. What if I did 4 theta over 12? Interesting. That almost looks like one of those limacons with an inner loop, but moved over. What if we did 5 theta over 12? We get this really interesting, it almost looks like some sort of a thing you'd find in nature or a thing you'd find in some really interesting artwork in a tiling structure. 6 cosine 5 theta over 12. By the way, just so that we're all aware, on this, all of these loops are contained in the circle of radius 6. I think this is a really neat and interesting looking object here. How about 6 theta over 12? not as interesting, but again, still enclosed in the circle of radius 6. 7 theta over 12 gives you another one of those really interesting looking structures. Again, I think this is a really neat looking structure. 8 theta over 12 looks like this. 9 theta over 12, we get this shape. 10 theta over 12, we get this type of shape. And 11 theta over 12 gives you this shape. Again, really interesting looking structure. Almost reminds me of sunflower seeds or something. And then 12 theta over 12 would be just cosine of theta, which we already know is a single circle. So with these fractional rose curves, we can get some really, really interesting looking pictures. All right. Now, I want you to recall that if we do cosine of just theta, we get a single loop. All right, we get a single loop. And when we did cosine of 2 theta, we got 4 loops. You may ask, well, wait a second, that means, is there any picture that just gives us 2 loops instead of 4? Well, sure enough, there is a way to do that, and that's to take something like the square root of, of 36 times, let's say, cosine of theta. I got to erase this other part. And then let's do cosine of 2 theta in there. So we can get a loop if we do something of this nature. Now, I chose 36 because we can see that it goes out to +6 and -6 if I have a 36 inside of there. Sometimes when people graph this, they'll write the 36 on the outside, but doesn't really have any effect. By the way, this should remind you of the infinity symbol. And in fact, it is a graph that looks like the infinity symbol. 2 loops going over to 6 and back to -6 in this sort of figure 8 fashion. Instead of writing the square root, oftentimes people will square both sides and write it like r squared equals a squared times cosine of 2 theta. So with the r squared on the left instead of square rooting things. And this is often phrased as a lemniscate. I might be pronouncing that incorrectly, but that's how I pronounce it, lemniscate. And a lot of these words obviously weren't US English words to begin with. So there it is. Again, a lot of interesting graphs. This lemniscate, these fractional rose curves, the standard rose curve where we have whole numbers times our theta. Then our limicons. Again, different types of those. Limicon with an inner loop, the cardioid, the dimpled, the convex. And then we obviously have the Archimedean spiral and then various circles. These are just some of the polar graphs that would be kind of hard to deal with rectangular coordinate systems. But with polar coordinate systems, they are pretty straightforward. So that is it on polar coordinates for this video. We will, in the next video, take a look at how to do some calculus topics with polar coordinate systems.